Hi everyone, we are from group S3S1. So in this video, we will explain about the verification, limitation, and the performance analysis for this assignment, which is the design and implementation of IoT petrol station with simulation with RTOS. So these are the outline we will cover in this video. So for this slide, this slide explains how we verify the execution time of our ISR. In video 2, we claim that our ISR is lightweight, so we performed an experiment using the STM32 SWB together with the DWT cycle counter. Diagnostic GPIO pin is toggled at the start and the end of the ISR, while the DWT counter records the execution time in CPU clock cycle. We repeat the test over the 1000 interrupt event, and the average execution time was about the 1.02 ms, with the worst case below the 1.2 microsecond. This result confirms that our ISR is lightweight and suitable for handling high frequency interrupt. So this experiment measures how long it takes for a pump signal from the peripheral STM32 board to trigger an interrupt on the main STM32 board. The peripheral board generates a 20 kHz pulse, and the latency is measured using the STM32 DWT cycle counter. After repeating the test 10 times, we obtain an average latency of 6.74 microseconds with very little variation. Since interrupt arrive every 12.5 ms when all 4 pumps are active, this latency is well within our timing budget and leaves enough time for the ISR and RTOS scheduler to operate correctly. So for next, this slide verifies that our RTOS architecture can handle the maximum system load. At 20 kHz, each pump generates one interrupt every 50 ms when 4 pumps run simultaneously. An interrupt arrives every 12.5 milliseconds, so the ISR must finish before the next interrupt arrives. Our measured ISR execution time is only 1 ms, giving that the 8.2% CPU utilization and leaving over 91% of the CPU available for the RTOS scheduler. We also verify that the event task always preempt the lower priority MQTT task. This ensures that the pump event and tank updates are processed immediately. So for next slide, this slide is explained about the limitation of our RTOS architecture. So the first limitation is the interrupt saturation. The system reaches its theoretical breaking point when the total ISR execution time becomes equal to or greater than the 12.5 ms interrupt interval. At this time, the CPU continuously service interrupt, causing the RTOS tasks such as the tank task and MQTT task to become starved. The second limitation is the network jitter bottleneck. Since the MQTT task has the lower priority, frequent interrupt cause it to be preempted repeatedly, resulting in delayed packet transmission and slower updates to the MQTT broker. The final limitation is the memory buffer constraint. If pump events arrive faster than they can be transmitted, the RTOS message queue eventually becomes full. Once the queue reaches its maximum capacity, a queue overflow occurs and causing the message loss. Finally, the experimental result confirmed that the RTOS architecture present in the video 2 performed as expected. The ISR executes within the required time budget, interboard communication is fast and reliable, and the RTOS scheduler correctly prioritizes the real-time tasks during the peak operation. Although the system has practical limitations under the extreme condition, this occurs only beyond the intended operating range. Overall, through a lean ISR design, atomic memory synchronization, and the proper RTOS priority mapping, the system maintains 100% data and integrity and zero miss the pump house under the peak simulation load. So that's all.